It's a pleasure to introduce today's speaker, Chelsea Walton from Rice University, and she will talk to us about quantum symmetry.
All right, well, I'd like to thank the organizers for inviting me to give a talk here. Thank you very much. So I'm hoping to keep this talk very down to earth. If you have any questions, please just shout. I'm not good with like the chat or the hands, so just talk if you have any questions or comments. So this is a talk about quantum symmetry, but in order to begin, I have to tell you what symmetry is. And Amy talked a bit about this in her JMN address, but I'm going to repeat a little bit of it. So what is symmetry? Symmetry is one of the oldest notions of mathematics. It appears in art, music, all over science. But mathematically, what a symmetry is as follows. Let's fix an object X, and a symmetry of your object X is just a transformation from X to itself that preserves the structure of X. And sometimes we might want this transformation to be invertible or reversible. So if we fix this object X and collect a bunch of symmetries of it, maybe even all of the symmetries, it forms a nice algebraic structure. Namely, it forms a monoid under composition, or the identity element is just leave the object alone. And if we want the symmetries to be invertible, then the collection of symmetries forms a group. So for example, if I were to take the object here, being a parabola, given by this equation y equals x squared, it's a nice shape, and the symmetries of it are, well, leave it alone and flip across the y-axis. And together, both of those symmetries are invertible and they form the group Z2. And then we have this lovely symmetric shape here, a star. Some symmetries include flipping across any axis or rotating by 2 pi over 5 radians. And those collections of symmetries form a nice dihedral group of order 10. Or we can take this nice continuous or infinite object here. It's a circle, as we know. And symmetries include flipping across any diameter and rotating by any degree. And together, the symmetries form this nice group. But in order to get into what quantum symmetry is, what I need to do is I need to translate the geometric notion of symmetry to an algebraic notion. So instead of talking about symmetries of geometric objects, I need to talk about symmetries of function algebras on the objects. Okay. So this is best illustrated for symmetries of affine varieties. Now, I'm not assuming anybody knows anything in this talk, so I'm going to define everything. All right, so what's an affine variety? An affine variety is just a shape that's formed by cutting out a bunch of polynomials equal to 0. So for instance, if I take the polynomial y minus x squared instead of equal to 0, I get this shape here. That's an affine variety. And as we saw up here, its collection of symmetries is a group Z2. But I can translate this over to the algebraic side by taking coordinate algebras. So the coordinate algebra of this whole space is this polynomial in the 2 coordinates x and y, polynomial ring in the coordinates x and y. And then I have to force this equation to be equal to 0, so I kill this ideal here. So the way that symmetries get encoded on the algebraic side is just via this group action. Okay, so it's a nice way of translating symmetries geometrically to symmetries algebraically. So this is really captured in the language of actions. Here I described an action on an affine variety and how it's translated to an action on the coordinate algebra or function algebra of a given shape. Okay, any questions? All right, so let's kick this up a notch. I want to use some fancy packaging to make this all very clear. What I want to do is encode this all into the language of category theory. I mean, basically, what this is it's a framework of relating one collection of objects and maps between them with another collection of objects and maps between them. I mean, a category is just nothing but collection of objects and maps between them. So what this allows us to do is to, in a really concrete way, shift the study of symmetries from a geometric point of view to an algebraic point of view. So for example, if I were to study symmetries of affine varieties, well, I can take the category of affine varieties, objects are affine varieties, and maps are regular maps. And I can shift this geometric study over here to an algebraic study by taking a so-called functor that sends an affine variety to its coordinate algebra. So in particular, its coordinate algebra is going to be a commutative algebra over C. And these gadgets form a category. Okay, and this is a contravariant functor, meaning that if arrows go in one direction on the left-hand side, they get reversed in the right-hand side. Okay, so what exactly happens? I want to translate symmetries or group actions geometrically to an algebraic framework. So I have my object X here, like a parabola or anything you like that's cut out by polynomials, and I have a group action on it, and I want it all this business to lie in this category of affine varieties. So in particular, we want our group to be an affine variety. It has to be formed by cutting out some collection of polynomials, or at least setting them equal to 0. So we have that G is an F object in this category. It's an affine variety, but it's also a group. So in order for G to be a group in this category, we need there to exist, maps in this category that play the role of multiplication, the identity, and also inversion, so that these maps are compatible in such a way that satisfy the group axioms. Now, if we were to push all this business over to the algebraic side here, remember, we do that by taking coordinate rings. Arrows, the directions get reversed, and this is done as follows. Instead of having a group action of a group on an affine variety, we then have a so-called co-action of the coordinate ring of G on the coordinate ring of our object. And all these gadgets here are commutative algebras. So in particular, OG is a commutative algebra, but it also has extra structure. Remember, on this side, G was a group, meaning that you had 3 extra maps that comes along with this construction. But now this gets translated over here to these 3 maps. So not only is O of G a commutative algebra, it comes equipped with a co-multiplication map, a co-unit map, and a so-called Antipope map that correspond to these maps over here. And the compatibility between all these maps satisfies so-called Hopf algebra axioms. Now I'm going to define what a Hopf algebra is very formally, but I just wanted you to see how it naturally arises. So the upshot is that classic symmetry, at least, this is captured geometrically by looking at group actions. Algebraically, this is captured by taking co-actions of commutative Hopf algebras. All right, any questions? Okay, so let's do some examples. All right, I have this geometric object here. Remember, this is my group that acts on it. I could translate all this business over to co-actions of commutative Hopf algebras on the coordinate ring of this gadget here. So in particular, the coordinate ring of this group is just, it's a group algebra. And the co-multiplication, co-unit, and antipode are given by these formulas here. But the example that we really want to keep in mind is the following. Let's not cut out anything. Let's just take a space, complex 2 space, and let's take symmetries of this space, but not any old symmetries, linear symmetries. So in particular, lines are going to go to lines. We want to leave the origin alone, and we want symmetries that are invertible of this complex 2 space. When we take the collection of such symmetries, this is really parameterized or captured by the group GL2C, the group of invertible 2 by 2 matrices. Now this is an affine variety. This is an affine variety because what do we need? We need the coordinates A, B, C, D, but we want to force the determinant to be invertible. So we throw in a dummy variable here and force the determinant to be invertible like so. Okay, so this group is a variety in complex 5 space. Now, we have that this group acts on this space by taking a matrix and, well, multiplying by a vector in this space and getting another vector. Now, algebraically, how does this translate over? Well, the coordinate algebra of complex 2 space is the polynomial ring in 2 variables, polynomial ring in the coordinates x and y. The coordinate algebra of GL2C is the coordinate algebra or the polynomial ring given in the coordinates like so, but we force the determinant to be invertible. And instead of having matrix multiplication over here, we sort of have like a matrix co-multiplication over here. As you can see, you get your matrix entries like so. Now, this is a nice commutative algebra. In fact, it's a commutative Hopf algebra with these given structure maps. Okay, so I didn't want to write down a formula for this. Okay, so the upshot is that classical symmetry, this is captured by group actions. Geometrically, algebraically, is captured by coactions of commutative Hopf algebras. That's all classic stuff, stuff that we can draw, okay? What is quantum symmetry? Well, this is a lot less understood, depending on who you're talking to. If you're talking, I mean, I'm going to present it from an algebraic point of view, but there's an analytic point of view, there's a topological point of view, there's definitely a physical point of view, and we're all going to give you different answers, but there are some commonalities. I will say that the overarching commonality is that you have to expand the notion of symmetry in order to understand whatever the objects are in your study. Okay, so I'll delve into this algebraically, and hopefully I'll convince you that we need to work beyond group actions in order to understand symmetry. Okay, so let's keep going. The basic philosophy is that the more sophisticated the object that we're studying, the more sophisticated the framework we need in order to capture its symmetries. That's the takeaway. So in order to at least get a start into quantum symmetry, I just want to talk about one example and just work it to the max. So oftentimes it's really useful to be able to have a quantum model for the complex plane. Now, I can't draw it. Nobody can draw. That's why I have these weird GIFs here. I mean, I literally just Googled quantum and these weird pictures popped up. We can't draw it, but we can still think about deformations or quantum deformations of complex 2 space, even deformations by just using one parameter. And even though quantum 2 space is impossible to visualize, usually what one does is instead study a good model of what its coordinate algebra is. So the coordinate algebra of the complex plane is a polynomial ring. And one might guess, or one might use as a nice model, a Q version of the polynomial ring as the coordinate algebra of this gadget. So through the lens of quantum physics, I mean, we can't observe quantum objects, but we can still make sense of them algebraically by looking at nice coordinate functions. Okay, so here's one example. So I have my complex plane here. I'm going to Q deform it, whatever that means. Algebraically, what this means is that I'm going to take the coordinate algebra of my complex 2 plane, and I'm going to cook up an algebra that still has the same vector space structure as a polynomial ring in 2 variables, but I'm going to alter the multiplication with a Q. So this is a very rough version of what a deformation is. So up here in the classic setting, I have a nice commutative algebra, but as soon as I start dealing with deformations, then I'm in non-commutative world, then I'm in quantum world. So I end up replacing the polynomial ring where x and y commute with a Q polynomial algebra where now yx is equal to qxy for q some non-zero scalar. This algebra here, this is a widely accepted model for a coordinate ring of quantized two space. And this is what we're going to study symmetries of in order to get a handle on this gadget.
Sorry, you said Q is a Q is a complex number, or is it just a dummy? Oh, sorry, there it is. Okay.
Yeah, but sometimes
Okay.
people just use dummy variables to do deformations. Yep.
Okay.
Yep. Any other questions? Okay. I write 40-minute talks on purpose, just in case there are questions. If there are questions, don't worry about it. You know, I write short talks, especially because of Zoom. People get tired on Zoom.
Well, could I ask how can you say maybe how this Q relates to the dummy variable t that you introduced before? Like how are with the GL2Z example that you gave, there was a t.
Oh.
I was wondering if you could just talk more about those two different things.
Yeah, so this is kind of dummy variable serves a different purpose here. So here it's just here to force the determinant to be invertible, but sometimes a dummy variable is used for deformations to, I guess, formally deform, like come up with a whole family of deformations, and then you specialize at t equal to some scalar in order to get one algebra. So that's a difference.
Thanks.
Yep. Any other questions?
One small question. Will this Q serve, sorry, hi. My camera is not on. Does this Q serve the same purpose as in quantum calculus, for example, defining this Q binomial, Q vector spaces, etc.? So is this what, okay, yeah, thank you.
Yep. Same Q. Okay. So now back to symmetry. Now that we have our object, we have a coordinate algebra of it, let's study symmetries. Now, in a nice framework, symmetries should commute with deformation. It should happen. So if I take an object and I deform and then take symmetries, I should get the same result as taking symmetries and then deforming. But this tends to break down when we just stay within the framework of group actions. So let's see how this works. Let's take my polynomial algebra. I'm going to Q deform it by forming this noncommutative algebra here with this Q multiplication. Okay. So that's a nice smooth deformation. I just take Q equal to 1 and I just perturb away a little bit to get this noncommutative algebra. Okay. Now, when I take symmetries of the polynomial algebra, well, let's just consider the ones that are linear, invertible, and preserve the origin. There's an algebraic interpretation of it. They preserve the gradient, etc. When we take the collection of such symmetries, we end up with the group GL2C, just like we had for the complex plane. But when we move away from Q equal to 1 and take the same type of symmetries now for this algebra, this group shrinks. It shrinks dramatically. So for instance, if I were to take the polynomial, the Q polynomial algebra at Q equal to -1, so yx is equal to now minus xy here. Well, I can only have that diagonal matrices and anti-diagonal matrices act linearly on such an algebra. And then if I move away from Q equal to plus or minus 1, I only have diagonal actions here. So this isn't nice. I mean, I have this nice smooth way of deforming an algebra, but over on the symmetry side, the group of symmetries jump around. I mean, and this makes sense because you can't really deform groups. I can't take a dihedral group, stick in a Q, and get another finite group, okay? So we need a bigger framework in order to handle symmetries and deformations. Let's study this now with Hopf coactions. Everything's going to check out nicely. So now I have, again, my polynomial algebra. I take a Q deformation of it, and instead of using group actions, I'm going to use coactions of commutative Hopf algebras. So now, before I had a GL2C action over here. Now I get a coaction of the coordinate algebra of GL2C over here. So this is the example that we had before. It's a nice coaction of a commutative Hopf algebra on this polynomial algebra. Now what's nice is that there's a very precise procedure to stick in Q's so that I get a nice coaction on this non-commutative algebra with a Q version of this coordinate algebra over here. And I can use the same rules for the coaction. And just about, I mean, most of the structure stays the same, except I have to deform the antipode. So up here, I have a nice coaction of a commutative Hopf algebra. And down here with the Q version, I have a nice coaction of a non-commutative Hopf algebra. When I deform and then take symmetries, I get the same result as first taking symmetries and then deforming. So when I broaden the framework from group actions to Hopf algebras, symmetries commute with deformation. Okay. So any questions on this?
So what does determinant sub Q mean?
Okay, there's a Q version of quantum determinant. Let's see. So, I mean, of course, up here, as you know, it's AD minus BC. Down here, it will be AD minus QBC.
Thanks.
Any other questions? Okay, so I hope I convinced you that at least we should think beyond group actions when we study symmetries, at least of non-commutative algebras or algebras that pop up in quantum physics. Okay, so that's a takeaway point. Just as group actions provide a nice framework for classic symmetry, or symmetries of function algebras of observable objects, coactions of Hopf algebras, these provide a nice framework for quantum symmetry, or symmetries of function algebras on quantized objects. That's why sometimes the term quantum groups appears in this study. Quantum groups and Hopf algebras, in my mind, are the same thing. Some people's minds, quantum groups are special Hopf algebras, but in my mind, they're the same thing. Okay, so if you're interested in a nice article that delves into this, Drumfeld has a nice ICM paper from 1986 on quantum groups. Okay, so now I have to tell you what a Hopf algebra is. I try not to start talks with definitions because I think they're boring. Let's start with a picture and then a definition. All right, so what's a Hopf algebra? We've already seen a bit of flavor of it. It's an algebra and it has 3 extra maps, but how exactly does it work? A Hopf algebra is a 6-tuple, okay? You have a vector space that comes equipped with a multiplication map and a unit map so that this triple forms an associative unidal C algebra. And you also have a co-multiplication map, co-unit map, so that this triple forms a co-associative co-unidal co-algebra. Basically, this is this gadget here with all the arrows reversed in direction. Okay. Now, whenever you have 2 structures and you're trying to stick them together, you need some compatibility between the 2. And you have these compatibility, if you have these compatibility conditions down here, this 5-tuple is called a bialgebra. So in particular, what you want is you want the co-unit to be multiplicative, you want the unit to be co-multiplicative, and you want your multiplication and co-multiplication to be compatible in such a way. I mean, what these diagrams mean is that if you basically any path from start to finish yields the same result. Okay, so far I've defined what's called a bialgebra. I didn't involve this map here.
By the way, what's the flip map on that pentagonal diagram?
Oh, so you just take the middle 2 entries and then just swap them. Mhm.
And do we have that because we need like commutativity?
Nope, you just force that to happen.
I see. Thank you.
Yep. So we don't need like a braiding. If you were thinking about braidings or anything like that, no, we don't. Well, we have that in category vector spaces. Yep. So we're allowed to flop in entries. Okay, so now we have an algebra, coalgebra, meshed together, that forms a bialgebra. And then we have this map that sort of plays the role of an inverse. It's called an antipope, and this is an anti-multiplicative map, and it satisfies some additional compatibility conditions, which I don't want to write down. Okay, so Hopf algebra is a very rich algebraic structure. And for those of you who don't like algebra, sorry, but it's a very beautiful structure, very beautiful. Okay, now I want to convince you why they're important. First of all, they're important because they generalize groups. They generalize groups. They're quite nice in that way. So if we take a finite group and take its group algebra, okay, we know what its algebraic structure is, its multiplication unit. It forms a Hopf algebra with these formulas here. Or if we take an algebraic group, which is a group and a variety at the same time, well, its coordinate algebra, we know what its algebra is. It also forms a Hopf algebra by taking the multiplication, the co-multiplication, co-unit, and antipope maps to be the pullback of the structure maps of G here. Okay, hello, doggy. Hello. Hello. I like animals. All right, so Hopf algebras are nice generalizations of groups. They broaden the framework of groups.
By the way, just in the first example, right, there are lots of groups where CG is isomorphic as a ring, right? CG and CH end up being isomorphic, right? But is this really a generalization in the sense that if they're isomorphic as Hopf algebras, then the underlying groups are the same? I mean,
oh. So
or was that just supposed to be, sort of an example to keep in mind, but it wasn't,
yeah, it's
literal?
just an example. Yeah, this is just an example of a group. Well, it's going to come back later. This is a very important example of a Hopf algebra. Yeah.
Okay. Yeah. All right.
Yeah, we're definitely going to see this later, though.
Okay.
Hopf algebras are also nice because, well, lots of people are interested in them. There's a very active classification program. Despite the fact that they actually contain the classification of groups, there's still a very active classification program for Hopf algebras. So they typically run in two tracks. There's a semi-simple Hopf algebras and the pointed ones. These are ones, the semi-simple ones are ones where any module is the direct sum of simple modules. So it's a very nice representation theory. Techniques from group theory are used to study such Hopf algebras, like their extensions and duals, and there's even like a Jordan-Holder theorem. There are lots of techniques from group theory that are used to classify these gadgets. On the other hand, we have pointed Hopf algebras that have a nice co-representation theory, if you will. So in this case, or by definition, the simple comodules are all one-dimensional. And actually, techniques from leaf theory are used to study these Hopf algebras. So if you read papers on this stuff, you'll see like Cartan data pop up a lot. I mean, that's usually used to parameterize such Hopf algebras.
What does dimension mean in this setting? I'm sorry to interrupt, but
no, vector space dimension. Vector space dimension. Yeah, thank you. Any other questions? Yeah, please interrupt because I don't know how to work the chat or hands or anything. Yeah. No, I guarantee if I try, I'm going to end up disconnecting. So okay. Third reason why Hopf algebras are cool. This is my favorite reason, even though, so if you're a grad student, you learn stuff after grad school. You don't have to know everything you need to know for life in grad school. I learned these words after grad school, and they've served me well. Okay, so they have a nice monoidal category of modules or co-modules, or representations or co-representations. What is a monoidal category? Basically what this is It's a category, collection of objects and maps between them that have a tensor product, meaning that I can take two objects and tensor them together and get a third object in the category. And there's a distinguished object that plays a role of a one. So this structure mimics the structure of a monoid, if you will. So if you see some random algebra walking down the street and you take two modules from it, you can't necessarily tensor them together to get a third module over the algebra. But you can play this game. You can do this when the algebra is actually a Hopf algebra. The reason why is because of these extra maps here. Okay, you're allowed to use them to give the category of modules a monoidal structure. So if I take two modules M and N, and I want to be able to tensor them together to get a third module. So what I do is I use the co-multiplication map here to get this vector space here. I flip across the tensor, and then I'm allowed to act in each slot. And that is my rule. That's my structure map for making this tensor product in each module. You use the co-multiplication. And likewise, I can give the ground field C the structure of the unit by using the co-unit map here. Okay, so it's very nice. It's a very, very rich representation theory. Okay, so given that, what exactly is an action, a co-action? Remember, because that's synonymous with symmetry. So if I take an algebra here, well, what do I mean by a Hopf algebra acting or co-acting on it? Well, once you have a monoidal category, you can take algebras in it because you can form multiplication and unit. So in basic terms, what I mean by an algebra emitting an action of a Hopf algebra is that this vector space is actually a module or co-module, and these two linear maps are H maps. That's it. So with this framework, we have that the polynomial ring, for instance, it emits a coaction of this commutative Hopf algebra, and this non-commutative polynomial ring emits a coaction of this non-commutative Hopf algebra here. All right, any questions?
Well, I'll ask one, just because I'm repeating a question that came up earlier. Before you said that we could think about Q either as being as an indeterminate or actually assign it a value. And what are do those two different points of view make it, have any impact in thinking about this coaction? You know what I mean? I mean, but think about the version where I want to have Q as an indeterminate versus, just specializing it for particular values.
So yeah, I definitely want to do, I want Q to just be a non-zero scalar here. If we made it like a dummy variable, we have to be really careful. Yeah, I mean, I might have to replace the C with like a C adjoin Q in a way. Yeah, actually, no, I have to be really careful if I were to work with a dummy variable. Yeah.
Okay. Okay, thanks.
Okay, thank you. All right, so now I want you that I've done something. Okay, I've done something. Some results. Let's talk about no quantum symmetry. So here's an interesting question. If you see an algebra walking down the street, okay, maybe I shouldn't say see, because maybe you can't see it, maybe it's quantum. Do you need groups, or do you need Hopf algebras to capture its symmetries, or will groups suffice? Okay, to make this precise, we say that an algebra emits no quantum symmetry if every action of a Hopf algebra must factor through something that looks like a group. So consider the following fact. If I have a finite dimensional Hopf algebra that's co-commutative, meaning that if I co-multiply and then flip across the tensor, I get the same thing as the original co-multiplication. So if I have a co-commutative finite dimensional Hopf algebra, it's a very nice fact that I end up with a group algebra. Okay, so we say that an algebra admits no quantum symmetry if every action of a Hopf algebra must factor through something that's co-commutative. All right, so you really don't need this fancy Hopf stuff to study symmetries of such algebras. Okay, so when do we have no quantum symmetry? That's the first question. One answer is that no quantum symmetry occurs when we act on commutative domains with a semi-simple Hopf algebra. So remember, there were two tracks of Hopf algebras to study, one that was studied with group theoretic techniques, one that was studied with Lie theoretic techniques. These are the group theoretic ones. So if I take a commutative domain, like a polynomial algebra, like a cube polynomial algebra, nice algebras, and I act with a semi-simple Hopf algebra, this action has to factor through the action of a group, essentially. Okay, so there's no quantum symmetry in such a setting. There are also generalizations, or I guess we can add on to this result. You can take deformations of, or certain deformations of commutative domains, like these Q polynomial algebras where Q is a non-rooted unity, Weil algebras, rings of differential operators. These are all nice algebras that share the same vector space structure of a nice commutative domain, but it has a non-commutative multiplication. And if I were to act with a finite dimensional Hopf algebra, I don't have any quantum symmetry. Okay. And this is not an exhaustive list. There are other examples too. Right.
I'm sorry. No. Okay, so these are these sort of like no-go theorems, meaning
No-go theorems, yeah.
we don't need, we can go back to groups for these?
Yep. Yep, they're
Yeah.
no-go theorems, yeah. So yeah, depending on your taste, some people dig them, some people don't. But yeah, they're kind of blockades. Yep. Okay, opposite direction. What about genuine quantum symmetry? What about Jesko theorems? Okay, if you're given an algebra, do we actually need a Hopf algebra in order to study its symmetries? So we say that an algebra admits genuine quantum symmetry if there exists an action of a Hopf algebra on it that doesn't factor through the action of something co-commutative. It doesn't factor through the action of something that's like a group. Okay. There are lots of examples of such results, but I'll just give you a few. So above, I said that, okay, if you act on a commutative domain with a semi-simple Hopf algebra, no go. You just stick with groups. But now when I take this other track and I act with something that's more Lie theoretic, then I get genuine quantum symmetry. So for example, if I just take a polynomial ring in one variable, and I take this nice small quantum group here, this finite dimensional quantum universal enveloping algebra of SL2 for being used to, okay. There's an action of this nice non-commutative Hopf algebra or non-co-commutative Hopf algebra on this polynomial algebra that doesn't factor through a group. Okay, so there are actually whole families of examples in this fashion. Another example that's in a totally different track was I can take something that's wildly different from a commutative domain, something that's non-commutative, definitely not a domain. Path algebra of a quiver. Now, what's a quiver? Quiver is just a directed graph. That's it. You know, just a bunch of dots and arrows between them. And a path algebra, this is just an algebra generated by the vertices and arrows of the graph. And the multiplication is determined by whether you can compose paths or not. If you can't, you get 0. If you can, it's a basis element. So there are very explicit formulas for nice examples of finite dimensional Hopf algebras that act on such combinatorial algebras in this paper. In fact, most recently in a paper, she's a grad student, Amre Oswald at University of Iowa. So I think this is cool stuff. Okay, Another family of examples is I can go back to my commutative polynomial algebra, and instead of like Q deforming or doing something ring theoretic, I could work homologically and take a collection of algebras that behave well homologically, like a polynomial algebra. These are called Artin-Shelter regular algebras. And what these are these are algebras that have finite global dimension, they have a Gorenstein condition. In some cases, they have nice polynomial growth. These are classified for small global dimension. And we have nice examples of finite dimensional Hopf algebras that act on these things. Okay, any questions on genuine quantum symmetry?
Do you can you compute the full group of quantum symmetries? Is that like or the algebra is, what does it form? Is it form an algebra, Hopf algebra itself, or?
Yeah, so every time I give this talk, I've been asked that question, so much so that
I didn't want to be that guy. No.
Yeah, maybe I should actually start doing this. So, okay, universal quantum symmetry.
Yeah, it's okay, Benson, you're not that guy. You're just isomorphic to that guy.
Thank you.
So is there like a biggest Hopf algebra? Is there like a quantum automorphism group? If I'm given an algebra, what is the biggest Hopf algebra that acts or coacts on A? Okay, so that's a very natural question. I mean, what is it? Another natural question is, for such a Hopf algebra, I mean, I said that the more sophisticated the algebra object, the more sophisticated the framework you need. Well, such a universal gadget should share some properties with the algebra. So for instance, if I have this nice discrete shape here, it has a nice discrete group of symmetries. I have this nice continuous shape here, it has a nice continuous group of symmetries. Something like that should happen for this Hopf action game. Also, there are generalizations of Hopf algebras out there in the literature, quasi-Hopf algebras, weak Hopf algebra, I mean, all sorts of generalizations. But one thing that I've been thinking about is, I mean, they popped up for various reasons, but I'm wondering, like, what are they good for symmetry-wise? Okay, so that's another question I've been thinking about. Okay, so in the last few minutes, I just wanted to talk about these three questions. What is the biggest Hopf algebra that acts or coacts on an algebra? We need to use coactions here. This is the best framework. And this is how it works. So if I'm given an algebra A, there's a Hopf algebra, which I'm going to denote by O of A, that's going to coact on A, let's say from the left. Okay. So that for any Hopf algebra that coacts on A, say from the left, so I have these two diagrams here, there's going to be a unique Hopf algebra map going from the universal gadget to H that makes this diagram commute. Okay, so this forms a Hopf algebra. It's huge. It might not have a finite presentation. It might be impossible to write down, but it is out there. Okay, it's a huge gadget typically. I'm going to call this universal Hopf algebra coacting on A. And sometimes to cut it down, you might even want to throw on some decoration, like you want Hopf actions to preserve the grading, for instance, of the algebra, or some other feature of the algebra, for instance.
Pardon me, may I ask briefly, what sort of algebra A do you have in mind here? Just any algebra? Or
any algebra? Yeah, any algebra. But I typically work with graded algebras. So for example, if I take a polynomial algebra, examples of the universal gadgets that, well, in this case, coact from both sides, are these coordinate algebras of these algebraic groups here. Okay, and what's nice is that this deforms nicely. So for instance, if I were to replace this with a deformation, oftentimes these universal gadgets come along for the ride as well. So this is all written up really nicely in a book of Menin, 1989 text. I highly recommend looking at the 2018 reprint. Really cool book. So there are universal Hopf algebras that act or coact universally. They do exist. Now, do they share nice properties of the algebras that we're coacting on? Oftentimes, yes. So for instance, if I were to take this Q polynomial algebra, and I take these universal gadgets that co-act on it, well, this is a nice algebra here. It's Noetherian domain. It has nice growth. And homologically, it's wonderful, has finite global dimension, nice injective dimension, etc. Do these algebras also share these nice features? And the answer in this case is yes. So a special case of this question was posed in a paper by Art and Shelter and Tate, 1991, by Menin. They addressed this question partially. The full question is not addressed. So there's still some work to be done here, and here's some references related to this question. But I mean, basically what this comes back to is that the more sophisticated the object that we're studying, the more sophisticated the framework we need to study its symmetries. Okay. And lastly, just the last question I wanted to get to is that there are generalizations of Hopf algebras out there, but what are they good for? Is symmetries of algebras that are still graded. I mean, if you notice, most of my examples are polynomial rings, which are graded. But polynomial rings are connected in the sense that the zeroth piece is just the ground field. We can get rid of that connected assumption and work with graded algebras where the zeroth piece is not necessarily the ground field. It could be something bigger. Okay, so for instance, I can take the direct sum of a bunch of connected algebras. That has a larger zeroth piece. I could take a path algebra of a quiver. The zeroth piece is basically the path algebra on the vertices. Okay, so that can have a degree zero piece of dimension greater than 1. And skew group algebras, smash product algebras, if you're familiar with them, these can be nice graded algebras where the zeroth piece are essentially the group in the Hopf algebra. Okay, but what about studying symmetries of these non-connected algebras? What I believe is that coactions of so-called weak Hopf algebras should handle these. So this is kind of a direction of work I started up, I guess, in the last couple of years. And so here are a couple of papers, and I'm still cranking away at this. But essentially, what a weak Hopf algebra is it's like a Hopf algebra in the sense that it's a 6-tuple. It has the underlying structure of an algebra and coalgebra, but the compatibility between these two structures is weaker. It's more complicated. The main example, though, is a groupoid. So just like group algebras are examples of Hopf algebras, groupoid algebras are examples of weak Hopf algebras. Okay, and anyway, that's what I've been up to. I like this stuff. It's been giving me something to do, and I hope you enjoyed the story. Thank you very much for listening.
Thank you very much.